Distributional robustness is an emerging topic in many areas related to data science, and we're delighted to have an awesome lineup of speakers. And we'll start this morning with Yao Xi from Georgia Tech. Yeah, so without further ado, I'll let Yao take the stage.
Good morning, everyone. So my name is Yao Xi from Georgia Tech, and it's a great pleasure to be able to come here, and thanks a lot for the conference organizer invitation to be able to give a talk here. Okay, is better? Okay, great, thank you so much. Okay, so today I would like to talk about several work we have done recently along the line of distributional robust hypothesis tests. Here's the agenda, so I'll start to introduce the background and then talk about two main formulations. One is based on the Wasserstein metric-induced uncertainty sets, and the second one is our recent effort trying to extend this to Sinkhorn, which leads to better computation compared to Wasserstein, and finally talk about some extensions for classification, which can be viewed as multiple hypothesis tests, probably in some extent, and online detection. Okay, here's the setup. The general hypothesis test can be cast as a decision-making process under uncertainty. And suppose we have two possible sets of distributions. And these distributions can be described by so-called uncertainty sets. So I'm borrowing the language from the robust and distribution robust optimization, as you can see the link in the next couple of slides. And so given a test sample, we would like to decide which of the hypotheses is true. And so we're going to make some assumptions about these uncertainty sets. In particular, these two sets are not intersecting, so there's no distribution in common across the two. So our goal is to be able to find the so-called detector or tests, which is a function that maps the observation space to the decision, which is in this case just two hypotheses. So it decides between one and two. And the goal is we want to minimize the risk, which is typically defined as the type 1 and type 2 risk. And this is, not to mention, a very classic problem in statistics and in the very basic statistical lessons. And we teach about Lemon-Pearson, basically simple hypothesis. If the two sets just consist of a singleton, so it can be shown that the best possible test, called the uniform UMP, uniform most powerful test, which minimizes the risk, which is type 1 plus type 2 error, is given by the likelihood ratio. Okay, so I put some pictures, find internet for Lemon and Pearson. And so this classic result is very useful and give us a guideline how to find the best test. However, there are some limitations because this only holds for singleton sets, means that if you want to tell apart two distributions, then likelihood ratio is the best. But typically, we are interested in not just tell apart two distributions, but possibly two sets of distributions for many reasons, because in particular, we can't specify the distribution in the exact form. And put in the nowadays context, that's because a lot of times our knowledge comes from data. So for the two uncertainty sets, two possible sets of hypotheses or distributions, sometimes we have data. We say I have training data or data collected for one hypothesis. We believe that we do experiments, for example, on a test whether or not a patient have certain condition, and there are data for the normal observations, and there are data for patients with certain condition, and now given a new test sample, we're going to decide which one of that is possible issue, is the patient sick or not. And so the data provide information. So how do we use that information? In the past, a lot of work has been done in assuming parametric form of the distributions and estimate the parameters. And so those are called, typically give rise to the parameter uncertainty sets. Okay, for example, you assume there are two Gaussians, and then let's estimate the mean and covariance matrices for each of the hypotheses. And more recently, people are starting interested in distribution-free setting, where we say let's don't assume any distributional form, but just say that the data provide information in the sense of empirical distribution, and the true distributions are possibly somewhere close to those empirical distribution. So we call those distribution robust methods. And so why we're interested in solving this problem is sometimes there are limited samples and sometimes imbalanced sample. A particular motivation I'm interested in is online change detection. And so we're interested in, for example, monitoring the health condition by wearable sensors. And so we have a tons of data for normal condition. But when something happens, an anomaly happens, and we typically don't have a lot of observation because we want to detect the change as quickly as possible. So we have a lot of data before the change, but after the change, there are very few samples. And so to make them more robust, given limited sample sizes, and if the data is high dimensional, sometimes we just want to use data themselves instead of casting distribution forms. So that's the motivation. And so quick literature review of what has been done. And so this leads to an interesting set of classic work called the robust hypothesis test, which has been considered by statistician Huber in the 60s. And he introduced this problem called epsilon contamination sets and saying, okay, let's take Newman-Pearson setting and saying that suppose instead of singleton, we have some epsilon small perturbation around nominal distributions. And then let's design a test that can work for these perturbation setting. And so those perturbations give us this, I draw a cloud, general sets of uncertainty induced by epsilon perturbations. And so he has a whole book, actually, that's written about the theory. And so is this good for our purposes? Theoretically, it provides some guideline, and also for the perturbation setup. But in terms of computation, it actually has some challenges, because if you look at the original framework, so the to solve this problem, finding the best detector for the epsilon perturbation for the general uncertainty set actually is difficult. It relies on finding the so-called least favorable distributions, which is a pair of distribution that's the worst, most difficult to detect or test within the uncertainty set. That gave rise to an infinite dimensional variational problem. In general, it's difficult to find. And for some special cases, such as univariate case, one-dimensional, there are analytical solutions. But if you go beyond one-dimensional case, even their original condition does not hold anymore, and so it's difficult to find in general. Okay, and so what makes us not interested in this problem and solving this is actually a recent work, fairly recent work by Golenberg, Juditsky, and Namrowski. Actually, they have two papers, 2012 and 2015. And so they find the connection between robust optimization and robust hypothesis test for the parametric setting. So they cast the problem as a robust optimization problem when the parameters belong to convex uncertainty sets. And so by looking at their work, in particular, actually, Arkady Namrowski is my colleague in the department and a great inspiration. And so he introduced me this work in the elevator, so I started to read his paper. And so, of course, not to mention there are many, many work around the robust optimization. These are the books, and also some recent papers using different formulations and also distribution robust setting. And this is Arkady's and co-authors framework. So consider distribution uncertainty sets that are parametric, convex forms. And so let's try to find the best detector. And so the risk for this in the statistical setting is usually type 1 plus type 2 error. So if we write this out, we realize what this is suppose there is some phi function. And so this phi is our tester decision function. And typically this compared with the threshold. For example, likelihood ratio is this form. And then the type 1 and type 2 error is basically the chance of making a wrong decision when one of the hypotheses is true. You make the opposite decision. And so to evaluate the chance of these errors, and so we can write it down, in particular, this is just average of the type 1 and type 2. We can also consider different weighted combination or taking the max. Those can be solved similarly. And so essentially, this type 1 plus type 2 error is induced by expecting the 0-1 loss function. And so if we try to find the best detector minimizing the risk, the first challenge is how do we deal with this 0-1 loss, because that's a non-convex function. So Arkady Namrowski likes convex optimization, so first convexify it. And so one approach is to find the upper bound of this, and the simple upper bound is exponential function. And so now we can formulate this problem as this minimax problem, which is to find the phi, which is the general detector, which can be arbitrary function, for the worst case, pair of worst case distribution in uncertainty set. Theta 0 and theta 1, actually, sorry, typo, theta 1 and theta 2 are the pair of distribution in the set. Okay, so we have this minimax problem, and now the phi is given by this convexification, so it is convex, and it can be shown now we have a convex saddle point problem. You can exchange the order of mean and max. And in particular, they've shown that the phi, the optimal detector, reduced back to the Neyman-Pearson results. You look at the log-heat ratio, and what is this pair for the pair of least square distribution? Now the least square of distribution is solved from the tractable convex optimization problem. If you look closer, what this is basically you find within the set of parameters, the one that are closest to each other with respect to the Hallinger divergence. So it also has a statistical meaning, which is interesting. And by solving this problem, since we have a convex upper bound, this also provides a upper bound for the type 1 and type 2 error that we care about. And this is one example what this looks like if we have a pair of Gaussians. And if the uncertainty sets are for the mu, you can see in the end, the optimal detector becomes a linear detector. And the pair of distributions, the pair of least square distribution, in terms of their mean, is finding a pair of mean vectors that are closest to each other in the Mahalanobis distance with respect to the covariance matrix, inverse covariance matrix. And the optimal risk is the upper bound for type 1 and type 2 error. So everything follows quite nicely. So now we're just saying, okay, can we solve this? Now for the non-distributional Gauss setting without assuming parametric form. And this is a joint work with my former student Li Yanxie and former colleague and now assistant professor at UT Austin, Ray Gao. And so we consider a similar setup, but now instead the uncertainty sets are induced by empirical distributions. And so how do we measure closeness to empirical distribution? We use Wasserstein metric, and I'll explain why. Not only it is popular, but it also has some practical reasons for that, I think. And so, as Alex Shapiro, one of our colleagues, suggests, you can have different metrics to induce this uncertainty around the empirical distributions, and we consider Wasserstein and also Sinkhorn later on. And so now we're going to use the lesson learned from Hakadi and co-authors and saying, let's first deal with non-convexity by finding some convex upper bound. So this is a small trick, and saying that instead of exponential, we can have all of these convex upper bounds you like. It can be hinge, scared hinge, and logistic loss. And what's interesting is that for these different upper bounds, there are different meanings in terms of finding this distribution later on. And so the second is how do we choose these uncertainty sets? So we can use KL. So there are work using KL for uncertainty sets already, and so nicely in these papers. And so we consider Wasserstein and Sinkhorn. In particular, it's because Wasserstein is a transport map. I'm sure many of you know that it doesn't require, you can measure the divergence between two distributions with different support. And this is something I think might be useful, in particular for a setting where limited samples. So this is the definition of the uncertainty sets. So we have two sets of training samples, and just imagine the empirical distribution is a band of nails, and just put a direct measure 1 over the number of samples uniformly at each of these points. So that is empirical distribution, and so we consider all the possible distributions that are close to this empirical distribution for the two hypotheses, induced by, measured by the Wasserstein metric. And so we can also set, say, the amount of tolerance or deviation we can have with theta k, so that's the radius. Okay, so like we mentioned, that Wasserstein may have some practical meaningful in this formulation because it can measure divergence between distributions with different support. And so this is the definition. And so I'm sure many of you have seen this before. It's also called Earth's mover distance. Just imagine you have two distributions. You want to transform one to the other. And you say, what is the minimum amount of work if you're an ant moving the dirt around to change one to the other? And the work is, the loss of that is, of the work is measured by the C, which is the transport loss. And so this can be defined for continuous or discrete distribution, continuous in general. And so compared with KL, so KL is typically defined, usually only for the ones with the same support. And so if we don't have a lot of samples, like I draw there, and so the true distribution might be this continuous curve, but if we don't have a lot of samples, there are gaps. Okay, those are the places there should, there's a chance of observing the sample, we just haven't observed yet. But if we consider an uncertainty set induced by, say, phi divergence, such as KL, then those places we haven't got any observations yet. And in an uncertainty set, those distributions are not included because of that. So at least the KL actually is excluding those, but with mass sustain, since it can measure transport, so we can move masses around, and so give rise to the possibilities of these places with gap. The observation hasn't appeared yet, and make this more robust. And so there might be a question, why not TV? Okay, total variation, that's another possibility. So I think in this particular study, we find that mass sustain also leads to tractable formulation, as we will show later. Okay, so finally, we have this formulation that we want to solve a minimax problem. This time, the P belongs to the mass sustain uncertainty sets around empirical distributions. And the first result we have is, for this general problem, you can see the phi and the P1, P2 in general actually are infinite dimensional. But they have a quite tractable result that first we have strong duality. We can exchange mean and max. So this one of these is easier to solve, in fact, quite tractable. And so the key idea in this is when we look closer, actually, the least variable distributions have a structural property that they must be supported on the unions of two empirical distributions, excluding the samples that are in common between the two. Okay, so that is the core of this proof for minimax. And because we can exchange the mean and max, in fact, we can solve this. The solution strategy is first for a pair of distributions, arbitrary P1, P2. We can find the optimal detector, similar to what Arkady has done. And second, that we can find what is the IFD, least variable distributions. Okay, that is the most difficult pair of distribution to detect. And because of that structure property, those IFDs turns out to be discrete, supported on the unions of training samples. Okay, and so because we have extended this convex upper bounds, and so we also find that, interestingly, for different convex relaxation, there are different optimal form of detector. For the exponential, it gave rise to Neyman-Pearson. For logistic, it's also log-likelihood ratio. But for hinge loss, this also becomes the sign of P1 minus P2. So sort of like look at the comparison, instead of taking the ratio, but look at the likelihood of the two and compare that. And remember, we said the least variable distribution is defined by the pair distribution closest to each other. When the convex upper bound is exponential, that is respected to the Hallinger distance. But for the hinge loss, it actually leads to finding a pair distribution that are closest to each other in the TV norm, total variation norm. So that's one thing. And this is actually the general expression of the optimal detector, but that's basically how we solve the form of these optimal detectors. And the next question is, now we have that for arbitrary P1, P2, but how do we find these variable distributions? And because of the, again, structural property, it reduces to a finite dimensional convex optimization problem. So finding a pair of distributions that are closest to each other in some statistical divergence, and then so this is the form of that optimization problem. So as you notice that this is almost independent of the data dimension in terms of complexity, because in the end we just need to form the pairwise similarity, in this case the L2 distance. Okay. All right, so this is summary of what we have achieved based on this idea. And in particular, we can also, based on this analysis, addressing the question saying, okay, we find that convex upper bound, then how we find the upper bound, we minimize the upper bound. So how does it compare to minimizing our original type 1 plus type 2 error? So we find this convex relaxation upper bounds, we can find that it's actually related to this phi function, which is used to find, basically related to the statistical divergence we have find associated with that relaxation. And so we can show that the loss is no more than this phi epsilon minus epsilon. And so if we look at the gap, actually, it looks like a hinge loss had the smallest relaxation gap, which is sort of like not surprising, because if you look at which function is closest to the L01 loss, then hinge seems to be pretty close. And so this is one example what the IFD looks like. And so, like we said, we want to use this because it can move masses around. And so this is On the left-hand side, empirical distribution, in this case, we only have 5 atoms for each distribution. You can see they're not overlapping, so we cannot take like the ratios. But then IFDS, now you can see in the middle, that's solved from this optimization problem. And it places masses on the points that are union of the 2 samples. Basically, intuitively, it says that for things that has appeared in the data set, either type H1 or H2, they're going to place some possibilities on that to make it robust. And one question, of course, maybe asked is, okay, so now if we use this LFD and plug that into our optimal detector, either likelihood ratio or the sign of P1 minus P2, but then if I give it a new test sample, it has never appeared in the training sample, and then how do we generalize? So the simple generalization is just say let's do a smoothing, convolve the LFDs with some kernel function, and that give us that generalization. But how we want to do better than that, just do a kernel smoothing. So actually that's what sinkhorn divergence is giving us to us. It gives us generalization to the whole space, as I'll explain. And this is an one result we can show that they give some consistency if we do a smoothing. And this is how to use it. Basically, you can see the nature of this method is if you want to test a class of 2 from a class of 6 images, then these LFDs are sort of like weights. They're placed on the 10 possible samples we have observed. And then if I give a new 2, then we have to do a kernel smoothing. I compare the 2 with the ones that are in the training samples and use these weights to form our detector. And so we can also show that, remember, the choice of the radius is important because the more we can tolerate the deviation from the empirical distributions, we basically make it more flexible, but we also don't want it to be too large. And so we can show that the optimal choice, so there's some optimal definition, is on the order of n minus 1 over d. And so there's a common argument basically says we want the uncertainty set to be large enough such that the true distributions are contained. But this is slightly different. In fact, we don't need the uncertainty set to contain the true distribution, but as long as it can contain a pair distribution, induce the corresponding optimal detector with a good performance. So that actually is a weaker requirement than requiring an uncertainty set to contain the true distribution, which can suffer from the curse of dimensionality. Okay, and so this is basically saying how do we generalize this to more than one test sample if you want to do a batch detection. So we can establish this guarantee, and then shows that if you have more test samples, of course, we can pool. This is the statistical pooling power, and decays exponentially fast with the number of samples we pool. Okay, and here's one simulation example. And so from this study, we find in particular this approach, like we have imagined, works most valuable for small sample setting because when the samples are small, and then we need this robustness. And so like I have advertised, we want to, in particular, initial motivation to use this for change detection, detect change quickly when we don't have a lot of samples for post-change distributions. So we apply this on real data with detecting human activities. And so this basically is a data set that has a variable sensor, measures 6-dimensional time series, and it records 6 kinds of human activities like walk, going up and down stairs, taking elevator, escalator, moving and still, and so on. So we want to detect transition of the activity as quickly as possible. And so this is an example what it looks like. On the left side, you can see the raw data from, this is from the jogging to walking, so before and after. So first of all, you can see this is one-dimensional. The distribution shift is a little bit hard to describe. Coming from a traditional change point detection literature, we usually talk about mean shift, covariance shift, but this is harder to describe if you look at before and after the change. And so on the top, that's the optimal detector. And in the middle, that's a classic statistical method, hoteling. And so when we compare this by large-scale experiment, so on the right-hand side, that plot shows detection delay versus type 1 error. So basically, you want to show which one has the smallest detection delay that can detect the quickest. So on the top, that's hoteling. And so this clearly shows the benefit of this robust detector approaches. And on the bottom, that red one is the optimal detector based on the hinge loss. So you can see that indeed, as the theory has suggested, the hinge loss might have the best performance because of the tighter relaxation. Okay, so I guess for the remaining 5 minutes or so, I would like to briefly mention the extensions and the current work. So, like we said, one of the things we're not quite satisfied with is the LFDs are defined on the empirical distributions of the training samples. Turns out because of that structure property. But how do we generalize it in a principled way? And so we find Sinkhorn actually gave rises to this, and it actually can compute pretty efficiently. So Sinkhorn is basically entropy regularized optimal transport. So this is the definition. I'm sure many of you have seen. So basically, on top of the optimal transport cost, we also have the digital regularization, which measures the transport map from the product of the two marginals. Okay, so this epsilon is the regularization term that controls the amount of regularization we want. So if epsilon is 0, then we go back to the original Wasserstein. But epsilon is very large. We're basically saying we don't want to go too far away from the product of the two marginals and make the transport map more smoothed and smeared. Okay, so it also has this interpretation. You can view this as the the coupling, find the coupling to not making the mutual information to be too large, minimize mutual information to some extent. Okay, and so I want to mention that this is particularly attracting because it can be computed efficiently, and has been suggested by many prior works. And so now we consider, for example, this is a work that's ongoing. We are solving the general Sinkhorn DRO problems. So as you can see, this formulation is different from the robust hypothesis test because in this case, there's one uncertainty sets, but the robust hypothesis has two uncertainty sets, one for each hypothesis. But just to show that for this case, I want to illustrate how the solution looks like, and it's quite simple. And so for some general convex loss, and again, I want to solve this mean-max problem. And so the uncertainty set now is induced by this entropy regularized transport, centered around empirical distribution with some radius r. And so, in particular, if we discretize the distribution P, okay, so suppose we have either a grid of points or generate some particles, and so we want to solve the distribution of the Z IFDS on these particles. And it turns out this can be solved, so some people call it light speed computation of Sinkhorn, so we have a similar kind of observation here. And this is different from the so-called matrix scaling solution, which is typically done in the solving Sinkhorn transport itself. Here we're not solving that Sinkhorn transport, but we're solving the LFD that gave rise to this min-max problem. And the optimal transport in this case have a closed form, almost closed form expression. The only thing that needs to be determined is this dual variable, which actually is just one-dimensional and can be solved from this line search. And so just give an example of how quickly this can solve the problem. Okay. And so, like I said, we're happy with this because it actually helps us to solve the generalization problem to the whole space. And so this is, again, the example where the two hypotheses have, only two atoms, and you can see that if now I can control the epsilon, which is the size of the regularization, and then the LFDs now are, if I make them larger, then LFDs are smeared into the whole space, and so defines our optimum detector. And so how does this give us, in terms of the performance? We also use this for example, robust portfolio optimization. And so empirically, Sinkhorn seem to have benefit of reducing the variance of the solution and achieving better solution empirically. And this is the performance comparison for the optimal hypothesis test. And so indeed, this one seems to work quite nicely. So that actually the lowest curve is our method. And so let's see, I have 10 more minutes. Want to mention a few extensions, a few things. This one is ongoing. And notice that, in fact, the Sinkhorn divergence defined in that entropy regularization form is not truly a divergence in the sense that a divergence needs to satisfy the property. For example, divergence to itself is 0. So in order to make this happen, we need to debias, and this is motivated by this work. And so subtracting 1/2 of Sinkhorn PP and Sinkhorn QQ. And this way, this can induce a true meaning divergence. And so it can be shown, we extend the argument in this recent paper that the Sinkhorn divergence is is convex. So again, we need convexity because we want to have all the nice properties. And so we can show that it's convex for P for a fixed Q. So in terms of our DRO formulation, this is useful. And then we can formulate a DRO with de-biased sinkhorn true divergence this way. And this is important because this experiment basically shows that if it don't do the debiasing, then the non-debiased sinkhorn actually it doesn't have the even doesn't have the monotonicity. We say that you have more departure, you want the divergence to be larger, but if you don't do the debiasing, it's not a monotone. And so it can be shown this is convex, and now we can again have the the intuition we had before that you can exchange mean and max. I just want to show some experiment we had. This is if we change the radius, what does the IFD look like? So this is basically, you can see when I change the radius to allow more and more tolerance, you can see how the IFD is changing with that. Okay, so finally, I want to talk about two possible related works. One is, a natural question is, now we're solving the offline hypothesis test and saying, given a new test sample, you decide which of the hypothesis is true. But I did ask the question early on. We said we want to detect this online. So the question is, initially, maybe there's one distribution, but there is a change after which the distribution is different. We want to detect as quickly as possible. This gave rise to the sequential hypothesis test. And so one way to address this is one of our prior work that we can define a so-called robust Q-sum, where we modify the Q-sum procedure, which is an online stopping time procedure, where the increment added to there is a log likelihood ratio. This basically is an optimal detector induced by solving the robust hypothesis test. And we can show some interesting finding, in particular that the ARL is average run length for the false alarm rate and expected detection delay. Now, instead of depending on the statistical divergence, they depend on these epsilon stars, which are the optimal solution, optimal risk solved by this problem. And so we're trying to extend this to the distribution robust optimization setting as well. And so what does epsilon star looks like? Sometimes they have explicit meaning, such as the parametric form. Okay. So another thing that we're trying to do now is, can we use try to use neural network to detect changes? And so in particular, we find that there's one way to do this. Okay, this is the question we're always wondering about, how to leverage neural networks to do hypothesis tests. Okay, so we find that there's one construction that can possibly achieve our goal, which is suppose we consider training of the neural network where the loss is designed as a particular kind of loss, which is the linear divergence between the two classes. And so as we train this long enough, and this divergence is going to give us to a decision. So compare this with the threshold, and if this divergence is large, indicating that the two distributions are different. So again, apply this to change point detection, and this seems to be working, detecting transition of activities. And so this way of looking at the difference, average difference in training loss after T iteration, can be related to a type of kernel MMD statistic. And so that also leads to performance guarantees. So that's the second extension. And the third one I want to mention is that I talk about hypothesis tests, which can be viewed as two-class classification. But what about multi-class? Is it possible to extend to multi-class? So we did consider this possible extension as well. In particular, we consider distribution robust k-nearest neighbor formulation. And so the difference is now that we need a different parametric decision form, a different way to represent the decision function. In particular, we consider k-nearest neighbor. Okay. And second is the loss is different because we have more than two hypotheses. So for k-nearest neighbor, it turns out that if we modify the vanilla k-nearest neighbor to allow weights on the samples, and we allow the weights to be different across different categories, then we can cast the problem as distributional robust problem. Okay, so this is a formulation. So you can see this familiar minimax problem where the phi is now the risk associated with our classifier. And so we can view the classification classifier as a random decision function So you toss a coin, you toss a dice with different faces, and each face has the chance of pi m x, and so that's our decision function. And so then the rest of it is following a very similar story that we can solve this optimal classifier induced by distributed distributions. Okay, and similar observation empirically that this works, very useful for small sample setting and also known as few shots learning if you don't have a lot of training samples. And finally, we also notice that it can be possibly extended to perform domain adaptation, so distribution robust domain adaptation in this recent post. So the last one is just a question, because I feel like this whole framework range all the way from statistic hypothesis test, which is a classic problem, but has a link to classification. And we explored some link in some way, for example, k-nearest neighbor, but there could be more links. So this is more like a question I want to toss to the entire audience, that can we use this framework, for example, to solve the GAN network? Because if you compare the two, there seem to be some similarities. So this is the GAN formulation, that it is also a minimax problem. So you can see the bottom line is here we're solving a minimax problem. We want to find the best detector against a pair of least reasonable distributions. And if you look at the GAN formulation, so the GAN is saying let's find the best discriminator. Okay, this case, in the worst case discriminator. Okay, the best discriminator that can tell apart the best detector versus the best generator against the data. So it's also solving a min-max problem where the G is the generator, the D is the discriminator. And if you look at the loss resembles the Shannon-Jensen divergence, and they did this as some motivation, and saying that this can probably relate to the classification error. And so if we compare this to the problem we're solving here, we're solving this type 1 plus type 2 error, and essentially, like we said, this different relaxation leads to different loss. And so question is, if we use those insights we have learned here to design better again, possibly, maybe change their loss function or different design of the problem, and is there going to be any benefits? So can we solve a distribution robust GAN problem? All right, so that's my last comment, sort of like a question. And so here's a summary, I think. So basically, we try to solve this kind of problem, which started to be infinite dimensional, but leveraging the formulation, and in the end, we can have tractable reformulations. So finding the phi, the optimal detector, for a pair of uncertainty sets for the distributions. And the risk here is related to the type 1 plus type 2 error, and we consider different relaxations. And there are many extensions, so I'll be very interested in discussing with you if you're interested in talking more. And thanks NSF for support. Thank you for your attention.
Hi, thanks for a super interesting talk. I was curious if you could say a little bit more about the least favorable distributions, their uniqueness of the detector. And you said that the least favorable distributions are supported on the data points, but are those the only possibilities, or could there be, so it's really a question of uniqueness of these least favorable distributions.
Right. That's a big question. So I think it may not be unique. So it is a convex problem, but it may not be strictly convex. Especially I think for certain relaxation like hinge loss, because you can see it has these flat places. So I didn't address that here, but that's a great question. I think it may not be unique. In fact, in the proof for the optimal radius, we leverage the fact that there could be a set of LFDs. And within the set of LFDs, you pick the one, a pair, that probably is giving rise to a similar performance in terms of the optimal detector. But I would like to say that indeed the form, the expression of LFD, I think that is unique. It's just the LFD themselves are not unique because they're not strictly convex problem. Yep, thank you.
Yeah, thank you for the awesome talk, and also all the background was great. My question's about the Wasserstein uncertainty sets. You characterize the optimal test, like given these sets that are constructed using the Wasserton uncertainty set. But did you, maybe I missed it, did you characterize the quality of the test or the performance of the test as a function of N1 and N2, the number of samples used to construct those sets?
Mm-hmm. Yeah, so that's a great question. So basically, statistical guarantees, I think, sample convexity. I think this work so far is mainly optimization kind of work. And so we say, how do we solve this optimization problem? But the quality of the solution indeed is an open question. I think we have some partial answer in terms of the radius. So that is closely linked to the answer to how do we choose the radius of the uncertainty sets. If it's larger, we have more uncertainty and more extensions. But I think ultimately we need to characterize the generalization errors of the solution, basically, as a function of the sample sizes. Yeah, that is an open question. Thank you. Thank you.